Hello, everybody, and welcome to another edition of Let's Talk ETC. I have a guest today that I'm sure is going to challenge all of us to think about some good stuff. I have with me Everett Hildenbrandt, and he's going to be talking to us about the KEVM, which is a project that we should all know about. And it leads to the K framework, which it's built upon. And so we'll talk about that and its impact to Ethereum Classic. So Everett Hildenbrandt is a PhD student at the University of Illinois in Urbana. He's currently on leave doing some contracting work for the Runtime Verification, which is the company that has been working on the KEVM, and he's also doing some contracting work for the Ethereum Foundation. So great stuff. And so, yes, welcome, Everett, to the show.
Thank you. I appreciate that. It's great to be here.
All right. So why don't you, tell us about your background, what you're studying in your PhD work, and how you got involved with blockchains. But before we get to blockchains, let's find out a little bit more about you. So
okay.
Go ahead.
Okay. Well, my undergrad was in Colorado, and I was studying physics, actually. But my junior year, I had a little extra time on my hands because I was doing a study abroad in Munich. And right around that time was you remember, Bitcoin has had these yearly, rises and then settles and rises and settles. And that was the $1,200 rise. You remember it went from 200 to 1,200 in a week. And right around then, I got pretty interested in these distributed technologies and stuff like that. So I decided to apply to grad school in, distributed systems. And I got into IOHK and decided to go there. But once I got here, I took some classes on distributed systems, and I also took a class in formal methods, which I'd never heard of before. But pretty much I fell in love with formal methods immediately on taking this class. And so I decided, okay, this is the direction I want to go. And I kind of left the distributed system scene for a little while. But then an interesting thing happened, actually. Andrew Miller, I didn't know him at the time or know of him at the time at all, but he joined at IOHK as a faculty, and he started this class on cryptocurrencies. And some of the students in the class approached me and said, hey, wouldn't it be cool to kind of do something in K with Ethereum or something like that? And I was like, yeah, that would be kind of neat. It would be nice to get back into the distributed systems kind of thing a little bit. So we just casually worked on KEVM for a little bit. And at the end of the semester, we had a very, very rough prototype, essentially. And then, it was a couple months after that, and we hadn't really done anything with it. And IOHK approached our group and said, hey, we'd really like you to, finish this project up and kind of turn it into a polished sort of thing. So we, that's what we did. We finished it up, we turned it into a polished thing, and now we're using it for all sorts of stuff. One of the main focuses being smart contract verification. So that's kind of the whole story up to how I became, a worker on KEVM.
Okay, so your original interest was distributed systems, and you thought that was your calling. And then when you got into grad school, you discovered that maybe formal verification was more to your liking. And so isn't that how it always goes? We don't always know the things that we're going to gravitate towards.
Yeah.
And then by
grad students, I tell them, hey man, in a year, you're not going to be interested in what you think you're interested in at all.
Right. So, and I also, I was doing physics as well. And there was a point where I had to decide if I wanted to go to grad school in computer science or physics. So I decided to stay the physics route a little longer than you. And then I did computer science afterwards. Yes, a lot of people that in this space seem to come from a physics background for some reason.
Physics sends its people to all sorts of fields. I think physics is very, there's also sorts of people in biology and in chemistry and all sorts of other fields from physics. So
Right. I think physics teaches you kind of to think broadly and get to first principles, which, of course, is applicable to lots of different areas.
Yeah,
But
totally.
yeah. So, all right. So then, how fortunate that you were able to combine your two interests, right? Formal methods, formal verification, and then distributed systems. And
Yeah.
so, yeah. Okay. And so you're on leave now. And how long are you on leave from your PhD program? Or is that set? Or
Well, right now it's set for just one semester plus the summer, so basically until August, and then I'll head back. I'm actually on leave for some kind of personal reasons, but it worked out fortuitously that I could kind of set up a contractor agreement because I'm not being paid by the university while I'm on leave, so I need to make money somehow.
right,
So,
right, right. Oh, by the way, this is just something to think about. Just to cause trouble. No, I'm just kidding. But so when I was in graduate school, some of the grad students would want to do internships with companies. And the idea was, look, I'm getting paid peanuts as a grad student. Isn't this great that I could go for the summer and right, make a little bit more money at
yeah,
a quote unquote real job? But then I had the counter idea. If I wondered if you do the math, right? Because after you get your PhD, you're going to make so much more. Your income is going to go up. So the equation might come out differently because if people do internships, they delay getting their PhD. See what I'm saying? So
yeah,
it looks like it's all positive, but if you're delaying the spike in your monthly income. So anyways, that was just a thought. I remember
yeah.
having that. And I didn't think a lot of people noticed that or thought about that. But either way, I'm sure you're going to do fine.
Yeah, I was gonna the leave happened independently of anything else, and then only after I decided to take the leave did I realize, hey, oh, actually I can also do a little contracting work and make some money, but I have to help my family through some issues right now, so that's why I'm on
uh,
leave. But
okay, yeah. So is this a hot field right now? Is that why, or what's the reason that do you think that, for example, the Ethereum Foundation, why did they uh, hire you to do some work?
well, specifically well, actually, it's not really clear what they want me to work on quite yet, but I went to DevCon 3, for instance, and I gave a presentation on KEVM, and I think that they are interested in the fact that KEVM gives an executable specification of the
Uh,
EVM because that is a lot easier to test for compliance with other implementations than the yellow paper is, for example. So
uh,
I think their main goal here um, is to kind of have both specifications, the yellow paper being a little bit more human readable and the
mhm.
KVM being executable so that they can more easily test that all the clients are in compliance with each other essentially.
Right.
And then also it makes it a lot easier to kind of prototype changes to the EVM, right? So you can change it on the yellow paper, but that doesn't immediately then give you a reference interpreter. But if you
Mhm.
change KVM, you get a reference interpreter out of it as well. So that's kind of the reason I think that the Ethereum community and the Ethereum Foundation are interested
Okay.
in this work. And then the reason that they specifically went with me is probably because I have been kind of leading the KVM project largely. So
I see. Great. Now, I definitely want to talk more about the KEVM, but maybe before we do that, we should introduce to the audience and spend a little time explaining the K framework. So, at the beginning of the show, I said that KEVM was built upon K framework. Was that correct?
yeah,
First
I
of
would
all?
say that's a good way to put it. The
Okay.
K framework is specific. It's like a toolbox for programming language builders is kind of how I would describe it. But
Hmm.
basically, it gives you a programming language for building programming languages in.
Hmm.
But the nice thing is, you can build a programming language in any language you want. I can take Python and I can use that to build an interpreter, to build a parser, to build all the different parts I need to have a
Right.
programming language.
Uh-huh.
Um, but with K, what you get all those tools. You get your interpreter, you get your parser, but you also get some formal verification tools because we built K around a couple logics called matching logic and reachability logic. You can go to kframework.org to get more information about that particular aspect. But basically what that means is you get a model checker, which means essentially a symbolic execution engine, as well as a deductive program verifier for free once you've built your language in our language. Whereas if you were to build your language in Python or in Haskell or in some other language, you would have to do extra work to get those extra tools.
Okay, that's funny you mentioned that. This is just an aside, but I've written my little small language in Python myself. And I'm sure that it doesn't pass. It's not up to the standards of the formal verification community. But so anybody that's listening, just to play devil's advocate. So I wrote my little language in Python, and I naively tested it on a few, I ran a few sample programs, let's say. So then if somebody like me is thinking, well, why do I need K, or what is K? You mentioned a lot of checks, right? But it looks like it works. It pretty much, works on the things I've thrown at it. So what would be the convincing piece, or, factor or whatever that would make people want to be motivated to do those formal checks that you're talking about?
Well, I guess first to back up a little bit, you might ask, okay, so, how long does it take to implement a language in Python versus how long it takes to implement one in K, right? That would be one question someone who is thinking, Python versus K would ask. And then another question they would ask is, if I write my interpreter in Python or in C, I can, get really good performance out of it by really hand tuning all the different aspects of it and stuff like that. And those are important questions to ask when you're asking someone in the industrial software development setting to switch to a new programming language or a new paradigm. And well, in terms of development time, I would say it takes about the same amount of time to develop an interpreter in K as it does in any other language. It took us a few, maybe 3 or 4 months of kind of just side project work, and then 3 or 4 months of intense focused work to build up the KEVM interpreter. And that was, I would say that's probably comparable to what it takes to build up something in C. And then in terms of performance, we're within an order of magnitude of the performance of the reference C++ interpreter implementation, which is pretty impressive given that we also derive some formal verification tools for you.
Right.
And then the second question, to get back to the question you actually asked, which is, what are these checks and the stuff like that we can do?
Yeah, what are they gaining for us? That's right.
Yeah. So for example, one of the examples that our project leader likes to lean on, because it makes us look good, of course, is this Open Zeppelin. Have you heard of this? These Open Zeppelin smart contracts?
It's my understanding is it's a library of very carefully written contracts that people have audited for security. And so the idea is that if people, instead of reinventing the wheel every time you write a complex smart contract, you use the Open Zeppelin components, and that could kind of increase the chances of writing an overall secure smart contract.
Right.
Okay.
Right. And so, in the process of, trying to prove to people that the KEVM is a valuable sort of thing, we have taken various smart contracts from the community. We actually started with one called the Hacker Gold one, which had a known bug in it, and we tried to verify that it met the specification of an ERC20 token.
Okay.
And in the process of doing that, we found the known bug, but we also found several other bugs, including some integer overflow, arithmetic bugs, and a couple other kind of minor things that probably wouldn't show up in practice. But integer overflow is a very real thing. And then, we kind of started the same process with the Open Zeppelin. We actually found some bugs with that, which I think have since been fixed. But what that goes to show is that, you can sit there and you can stare at a contract all day and not find bugs in it. But as soon as you try to actually verify that it meets the spec, the verification won't go through unless the contract actually meets the spec. And in the process of doing that, you find these these kind of discrepancies between what you think the contract is doing and what the contract is actually doing. So at that point, you have to either go back and say, okay, there's something wrong with our spec, as in we expect something out of the contract that we shouldn't be expecting out of it, or there's something wrong with the contract, and then you have to fix the contract. So even if you have these extensively human audited contracts, you can still benefit from going through the process of doing the verification, because in that process, you likely will find bugs. And if you don't find bugs, then you have checked it, you've proved it,
Right. Yeah. And if we had to summarize why the use of K framework was able to find those bugs, is it because in addition to specifying, or in addition to writing the software, you're forced to specify the semantics? Did I understand that correctly?
Yeah, roughly. So there's a couple different components that go into it, which can kind of lead to some confusion, but there's the semantics of the programming language itself. So that's what KEVM is. And then from that, you kind of push a button, and what you get are a bunch of separate tools. One tool that can just parse programs, one that can interpret them, another that can do deductive verification, for instance. So the deductive verification engine will take in as input kind of a specification. The specification usually reads something like, starting with this program, or in this case, this smart contract, if I execute it from the beginning with these arguments, then this change to the global network state will happen at the end of the contract.
So Everett, can you try to keep it as, like, explain it like I'm 10 years old, I guess people say, or explain it like I'm 5. So what's the essence of why the K framework helps people to write less buggy code? Can you take a stab at that one?
Yeah, sure. So the K framework, in its overall nature, is just that the overall viewpoint of the people on the K team is that, if you write a debugger, if you write a interpreter, if you write all these things, you should only have to write that once, and then you kind of instantiate it or make it specific for the programming language of choice, right? So, there's all sorts of tools out there. There's like IntelliJ, which is this huge, IDE specifically for Java, for instance, right? And then the C# people have their own .NET stuff going on, and I don't even know, like Python has its own IPython notebooks or stuff like that, right? And they're all these amazing tools, but they're all specific to one language, right?
Okay.
And the idea of the K framework is that you should write those tools once, right? And then you should be able to take that same tool and instantiate it to each individual language.
Okay.
So what we do, go ahead.
Oh, we talked before this show, and I remember asking you, because this was something that was confusing me. I had the idea somewhere that the K framework somehow writes all your code for you. And so, but apparently that's not correct. But so one of the things you're saying that, yes, it doesn't write all your code for you, but it comes as close as it can. It writes a lot of this. It avoids a lot of repetition.
It does try to avoid repetition. It wouldn't avoid any repetition at the level of writing smart contracts, for instance. You still have to go out and write your own smart contracts. You still have to go out and write your own C programs, for instance. But what it does avoid the repetition of is, I've written an interpreter for Python and I've written an interpreter for C, and they're completely different code bases. Well, that's kind of a shame, because the basic principles of an interpreter are the same across languages. So it'd be nice if you could write one interpreter and then instantiate it to each individual language using a kind of standardized sort of process, which is what K does for any programming language that you have a K semantics for. And then, of course, we go on beyond that. We don't just derive.
Okay, so let me start. So instead of you have a lot of overlap between programs, and so with the K framework, you can reuse parts easier.
I would say not between programs, but between programming language tools, right? So there's a bunch of tools you want around a programming language. One being, for instance, a debugger. You want to be able to sit there and step through the execution of any given program using your debugger by hitting next, 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 and seeing how it changes the state. So for instance, we have in K a language independent debugger, which means that it's a debugger that once you give it the K semantics of your language, then it's a debugger for that language. So then because we have a K semantics of C, because we have a K semantics of Java and JavaScript, we get a debugger for all those three languages as well.
So the reason for the ability to apply it to other problems is because of this standard language, the K framework language that's being used in more venues. Is that so? It's a standardization of the language used to create all of these tools, all of these programs.
I'd say, yeah, roughly, it's a standardization of the language used to describe programming languages, right? So we have,
instead of doing every language specification in a different language or a different system, right? That okay? Okay, right. All right, and then and so certainly having a standard language helps, but it's much more than just having a standard language, right? Because we could all decide tomorrow, hey, everybody has to define every language in Python,
right?
And that, right. I mean, but that you would disagree that the K framework is equivalent to that, right?
Right. So, I would disagree with that, and it's not, and you're right. It's not because Python's not a standard language. You could certainly decide, okay, Python's going to be our standard language for defining, programming languages in, but the benefit that you would lose from moving to K to Python instead would be that K has solid mathematical foundations in reachability logic and matching logic. So you can take a K definition and interpret it the same way you would interpret a Python program, just by executing it, for instance. But you can also take a K definition and interpret it more like what you would interpret, I'm trying to think of a good analogy here, but I would like the closest thing that's coming to mind is something like a model that you define in Coq or Isabelle, some of these theorem provers. You can essentially give the K definition a rigorous mathematical semantics in terms of matching logic and reachability logic, and using that semantics do direct mathematical reasoning over programs in the programming language.
Okay, so to keep it simple for me and my audience, I think one of the things I think what you're saying is that the K framework language is much more amenable to analysis than Python. Yeah. Okay, but then to play devil's advocate, a lot of people say that Haskell, right, functional programming, that there are languages that are more amenable to analysis. So is that just a halfway step, or how would simply using a functional language that has good mathematical properties like Haskell compare? Would that be good enough?
Well, certainly using Haskell, I think would get you a lot closer than using Python would be, because you could make good arguments that Haskell has mathematical models just as much, or at least maybe some subset, maybe like core, like GHC core or something, has mathematical models. In fact, we're working on a K semantics of GHC core, although that project's been put on the back burner a little bit.
Okay.
But yeah, so I guess I would say, in terms of the K versus Haskell debate, our whole group kind of has a soft spot for Haskell, so we're not going to, hate on Haskell too much. But but the main
I guess I asked a good question. I had no idea. I was just throwing that out there that Haskell was even okay. So you're saying that there has been discussions of what I was saying of why not Haskell, versus K.
So for instance, Haskell has kind of a derivative language called Curry, which allows you to do essentially symbolic execution with Haskell. It uses a narrowing engine, which is pretty similar to what K is using to do its symbolic execution. And that right there already gets you, 65% of the way to being able to do this kind of mathematical reasoning. But the difference between Haskell and K is that in K, the math came first, right? So first, people sat down and they prototyped the math, which is reachability logic and matching logic, to
Mm-hmm.
kind of figure out what a good logic for describing programming languages would be. And then the tool K was built using that math, whereas Haskell is kind of more, the programming language came first and people are coming in afterwards and trying to give it mathematical models.
Mm-hmm.
So we already
Okay.
have a solid mathematical model of K. We already know that we can do sound and complete reasoning, or I should say relatively complete reasoning to do deductive verification using K. Whereas for Haskell, you would have to come in after the fact and try to build up that mathematical model. And people have tried, but to my knowledge, I haven't seen a full mathematical account of the whole Haskell language. So that's one thing we're trying to do, is give a mathematical account of at least GHC core, which is what Haskell is compiled down to in K.
Right.
But like I said, that project was kind of put on the back burner a little bit for some other unrelated reasons. But.
Right. There's lots of other work going on that's been pushed to the forefront, so it'll probably get done eventually, but it hasn't been forgotten, you're saying.
Yeah, no, and we made good progress on it. It's just that the people had to be reallocated to other projects. So.
Okay. Now, I don't dispute, and I can believe that there is this that if you develop something in K framework, it's designed from the get-go to have solid mathematical foundations, and it'll be more amenable to analysis. But it doesn't seem, or it seems like you would have to pay a price, that you wouldn't get that for free. So like Python is very easy to program in. It's very user friendly. But if I said, okay, fine, K framework sounds like the way to go for security, you're saying it's not harder to use the K framework versus someone's favorite user friendly language? That seems too good to be true.
Well, of course, there's a learning curve to K, but pretty much I would say, 30% of the language just kind of boils down to a run-of-the-mill functional looking programming language.
Mm-hmm.
And I can't remember the exact number, but I want to say maybe around a fifth of the KEVM definition, for example, is just purely functional. So a large part of K you can get just by that. And then the rest of it is just, the standard kind of learning curve that you have when you're learning any new programming language. But after that, I would say that it's as fast to develop a prototype in K as it is to develop a prototype in Haskell.
Okay.
So for instance, there's a simple programming language called IMP or SIMP, depending on who you talk to, which is just, it has like variable assignment, variable lookups, a simple expression language like, plus and minus and times, and then also Boolean expressions, and then if then else, and it also has while loops. And, in Haskell, I've written an interpreter for this. And first you have to write the parser. So you got to pull out your parsing library and write the parser.
Okay.
Second, you have to write the evaluator, right? And then all told, you probably are looking at, a couple hundred lines of Haskell code. In K, we have a tutorial for IMP, and it maybe is 80 lines to get the entire IMP language up and running. And you don't have to worry about writing your own parser. You can just write down the grammar directly. And the transition rules, the evaluator is usually a little bit easier to write than the Haskell one is.
Well, I'm guessing that's because you have useful libraries. So you're taking the same attack as the Open Zeppelin guys, which is making reusable components.
Actually, it's not. There's not any libraries that are used in IMP other than a simple.
Well, I mean, in your tools, the reason you're saying you could, what you're saying is you could implement IMP faster and with less code using K.
Yeah.
And the reason is because you have components that they're.
Well, it's because K is a language that's specifically designed for describing programming languages. So, for instance, if you were to write IMP in Haskell, you're going to have to spend a bit of time just writing the parser, for instance.
Yeah.
And if you're picking Parsec or a library like that, that's doing some sort of recursive descent parsing, but it's not a GLL library, that means you have to do a bunch of grammar factorizations and stuff like that just to get it to the point where you can even recognize proper IMP programs. Whereas in K, you just describe it in a normal kind of EBNF grammar style, which
Okay.
everyone thinks is very readable and it's very compact. And then we just kind of take care of all the parsing stuff for you. So
yeah, but I mean, I'm sure you know that there's tools, right? Even a primitive language like C has there's Flex and Bison.
yeah.
Yeah,
Yeah, so most of these tools still require that you, for instance, factor the grammar, and usually this leads to well, in the worst case, it usually leads to an exponential blow up in the size of the grammar, for instance.
okay.
But usually you don't hit that exponential wall. Usually it's just a little bit of a blow up in the size of the grammar. But either way, it's just more effort on the part of the user, right? Like
Right.
you have to sit down and think, okay, how do I get rid of this left recursion? How do I get rid of this hidden left recursion in the grammar? And then you write down the parser according to that. But in K, you just write down the EBNF thing, and then we have a nice GLL parser on the back end that takes care of all those different cases for you.
So you're just the same way that there's low level languages and high level languages. So K is at a higher level.
Yeah. So you wouldn't do systems programming with K.
Yeah.
Although we're experimenting with some stuff like that, but it's a little more painful than doing systems programming with like C or something like that.
Yeah. All right. So here's this might be a dumb question, but all right. So I think it's pretty clear that K framework is a solid language to specify things in, to write languages, write virtual machines in, and the fact that you were able to find bugs in the Open Zeppelin libraries when there's supposedly security experts of it, you can't argue with that. So then the big question, the reason everybody gets a lot of times are forced into thinking about formal verification is right. They have software that has to work. Yeah. Maybe it's a life and death situation. So by using K framework, is it too outlandish to say that you can guarantee that you're not going to have bugs, you're not going to have issues? Are we at that point yet?
Well,
or is that asking too much?
Yeah, I mean, that's really asking too much of any verification tool. The reason being, a lot of people, when they think of verification, they think, okay, I just hit the verify button and then boom, my program's verified. It won't have any bugs. But
right, absolutely. That's what I want. That's the holy grail, right? That's what we need is to know. Does my software work? Yes or no? I want a binary answer.
Yeah, but the problem with that question, I mean, it's an ill-formed question, really. Like the problem is that you have to say, instead, does my software have this specific property, right? You can't say, does my software work, and hope that the computer will know what the word works means, right? So I've seen, especially in the smart contract space, I think because there's a lot of money involved in the space, and there's a lot of motivation of people to kind of be the first on the market or something like that. I've seen a lot of people who have given tools that say, okay, all you do is you hit the verify button and then boom, your contract is bug free if it says it's bug free. And that's really kind of misselling what formal verification can do, because if that's what they have, then what they're checking is for some fixed class of bugs, right? They might check that, okay, integer overflow can't occur. Okay, word stack size can't be overflowed, can't be underflowed, a bunch of very specific checks, right? But all those checks put together might not mean that your program is behaving how you expect. So when you say verification, you have to say verification with respect to a specification, right? So if you want to do verification, you have to both come to the verification engine with the program you want to verify and the specification that you want the program to meet.
Okay.
And a lot of people who aren't, in the verification world or in the formal methods don't realize that there's that second part you have to come to the verification engine with. They just hope for kind of the verify this button that they can click.
Yeah, that's what I'd love to have. Yeah. Okay, when you talk about this second specification, is that what I was referring to as a semantic specification?
You could call it like a semantics of that particular program, for instance.
Okay.
So like the KEVM is a semantics of the EVM, which means it's a specification of the EVM itself. So that's not a specification of any particular smart contract.
Okay.
But then you could say that a specification of what you want the smart contract to do. So you could say, like, I want this function of the smart contract to only transfer value between these two accounts on the network if, it doesn't send either of their balances negative or something like that. So it might be a token contract.
Right.
that would be a specification of that function of the smart contract. You would be saying, this is the behavior I expect of this function. Please tell me if there's any way this function cannot behave in this way. If there's some way it can misbehave.
Right. So the semantic specification, or what you call the specification, whatever we call it, that's just a way to. So when the question I asked a few minutes ago was, I wanted a button, right? Everybody wants a button that they could push and say, does the program work? Yes or no? Mm-hmm. But the semantic, and you said that was an ill-formed question, but the semantic specification is really a way to ask the right question, right? It's a way to ask that in a legitimate way.
Yeah. And often it's not like you develop the program and then you develop the specification independently. You kind of develop the two together, really, is what ends up happening. Because, for instance, with this HKG token, we started out with what we knew was the buggy version of the token, and then we wrote what we thought was an appropriate specification for the contract. And writing a specification is usually not trivial, right? It takes a little bit of time and some thought to do.
Yeah.
And then we asked, the K verification engine, hey, can you verify it? And it came back and said no. And then it told us the reason. Essentially, it gave us a big formula saying, like, this is the reason. It's because I can't prove this. So we looked at that formula, kind of scratched our heads a bit, and then we said, oh, okay, it's because of this bug we knew about, right? So we went and fixed that bug we knew about, asked it again, and it still said no.
Now, when you say there was a bug, this was a bug in the semantic specification?
No, in the program itself.
Oh, okay. Okay, gotcha.
Yeah.
Okay.
So then it still said no, for instance. And then we looked again and we realized, oh, hey, there's an integer overflow issue right here, which is what the prover kind of told us, but in its very cryptic way. And then that was a bug in our specification, or at least that's how we chose to fix it. We could have fixed it by fixing the contract, but we fixed it by changing our specification to say, okay, and this function will never be called with an integer that makes this particular operation overflow. So in that way, we kind of, incrementally design both the program and the specification together until we get to the point where we have a specification that is verifiable for the program.
Right.
And that when the humans look at the specification, they're happy with what it says, because you could easily arrive at something that you're unhappy with.
Right. So I think I understand now. So the specification, the semantic specification, whatever we call it. So the K framework can guarantee that a program does adhere to that.
Right.
Okay. But what you're saying is that that's not necessarily all that you need to worry about, right? You might not have the right semantic specification, or it might not. Okay, so
you might have a trivial specification. You might write a specification and you labored over it for hours and hours, and then you realize, oh crap, my specification actually doesn't say anything. It says, I don't care what program it is, or something like that. It might say anything can happen. Your specification might just be some trivial specification that's met by any program, and then at that point, of course, you can verify.
Right. So now then the challenge is, so the challenge ultimately then is to have an accurate, complete semantic specification.
Yeah, something meaningful.
That covers up. Okay. I think we've given a great introduction to the K framework. And again, as for people that want to learn more, you gave out the website kframework.org. So now why don't we talk about the KEVM? So that was applying all the firepower of the K framework to improving the security of the Ethereum Classic, Ethereum virtual machine. So why don't you kind of now segue into that and describe what's going on there?
Okay. Well, like I said, kind of in the background or history section, it kind of started out as kind of just a side project that a couple of us were interested in. And we work in the K group, right? So of course we're going to use K. We could have also chosen another language called Mod, or even one of these theorem proving languages like Hawker Isabel or something. But we're in the K group, so we chose K. And at first we didn't really have many aspirations. It was just a kind of a fun sort of side project for us to do to kind of test the limits of what K could do. But now that it's kind of actually a full-blown formal model of the EVM and people want to use it to verify that their smart contracts meet some specification, we have, we're a little bit, we're burdened with the process of, maintaining and making sure that it is kept up to date with all of the updates that are rolling out for Ethereum. So actually, the original KEVM, it only supported one execution mode, which is, I think, the same execution mode that Ethereum Classic uses, but now it's actually modal, so you can say, okay, I want to put it into the EIP 150 mode and execute using that. So we can essentially execute it using the different modes that the network has gone through, which means that it'll be pretty easy to update it as updates are rolled out for
that's good.
Ethereum.
Okay.
Which might contradict a little with the code is law sort of mentality, but not everyone feels that way. So
now, also, if for some reason, so I think you might have just answered my next question. I was going to ask you if people wanted to make changes to the virtual machine, the opcodes, for example, if it was easy or trivial even to add that to your KEVM work, and it sounds like you're saying that it's
yeah, it's very easy actually. We can have even just different versions of the same opcode within the same semantics, and then you just tell it when you run the program, okay, I want this version. So EIP 150 or Byzantium or now the new one coming out, I guess, is Constantinople. We don't have full support for Constantinople yet, but yeah, basically we tried to make it so it's kind of easy to specify, from the command line which particular version you want.
Okay, and now you've already addressed this, that the K framework doesn't just automatically write code for you. So just to be clear, the KEVM specification, you don't get out of having to implement the virtual machine in whatever language you choose, right? It doesn't do that for you automatically.
Well, so the KEVM does act as a virtual machine. Like, you could run it on the network and process smart contracts with it. It's a little bit slower than the other ones, not that much slower, but it is a little slower. But it will not generate, right now what it does is it generates OCaml code, and then that OCaml code is used. So you could say it generate, if you want an OCaml interpreter of the EVM, you could just take KEVM, ask it to generate the OCaml code, and then just take that as your OCaml interpreter. Now, the code it generates is not very readable because, we essentially have a slightly custom OCaml compiler that is able to kind of optimize for cases that we know show up a lot based on the type of code we generate. So I wouldn't say that would be a good way to get a good OCaml interpreter, but what you do get out of it is a binary that can act as a virtual machine essentially for you.
Now, if the K framework in the general case doesn't automatically write secure code for you, so how come in the case of your KEVM work, why was it able to generate the virtual machine interpreter?
Well, so there's a difference between writing secure smart contracts and writing a virtual machine, right? So for example, we have the semantics of C, and using the same process, we get an OCaml interpreter for C that is correct with respect to the semantics. Or we have a semantics of Java, and using the same process, we get an OCaml interpreter of Java that's correct by construction. But what you don't get is a tool that will write smart contracts for you, right? So there's the difference between writing the EVM itself, writing a interpreter for the virtual machine, and writing smart contracts.
Okay, so the K framework can automatically create interpreters that you specify in K.
Mm-hmm.
Okay, well, that's pretty good. Okay, now, and one last question. Well, we can, if you want to say more, but so the K framework, or in this case, KEVM, so it barfs out this interpreter based on your specification.
Yeah.
Is there any danger that interpreter is not going to follow the specification exactly?
Well,
how confident can we be?
We can be as confident in that interpreter as we've tested it, essentially, and we've tested it extensively using the same test set that is used for all the other Ethereum clients, essentially. So there's the, the Go Ethereum client, the CPP Ethereum client, Pi Ethereum, a couple others. I kind of lose track. But they all test against the same test set, which is at github.com/Ethereum/tests. And right now we're running the vast majority of those tests essentially on every pull request in the master. So if you're on the master branch of the KEVM, you can be sure that it is complying with the other interpreters out there that exist for Ethereum.
Okay.
So at some point you have to ask, like, does that mean you actually are complying with the specification? And at the end of the day, the specification is written down in English, so it's not really clear how you could be sure that it is.
Right.
But the best you can hope for is that it agrees with all the other implementations out there.
Yes.
And the answer to that question is yes, it does agree with the other implementations out there.
Well, actually, I would think okay, yes. So one way to make sure that an interpreter is correct is make sure it agrees with all the other interpreters. But you're making now a new road, which is if something like the K framework can barf out an interpreter for you, that you have mathematical arguments, proofs that it is correct.
Well, so once again,
better.
Correct here is again ill-defined. You could say it's correct with respect to the K code you write, but of course it's going to be correct by construction if that's your definition of correct. So I think really
it's going to be correct with respect to the semantic specification. How about that?
Yeah. So that will be true by construction, but that's not really a useful property for most people. A more useful property is, does it agree with the other interpreters? Because those other interpreters are going to be the ones at the end of the day that decide how transactions get processed on the network, right? And so if your formal model of the EVM is not agreeing with those interpreters that are actually processing transactions,
right,
then you could go and do a proof with your formal model, and that proof might not actually carry over to the real world. It might be that you think that your contract is secure, that some property has been verified about it, and then you go to execute it on the actual blockchain, and something goes wrong, essentially. So It is important that the KVM agrees. It's more important that the KVM agrees with other interpreters than that it agrees with the yellow paper, actually. So
I think I understand now what you're saying. So it's these other interpreters came first, and so nobody's able to take a K specification and say, okay, this is going to supersede all the software that's existed before this. So you're forced to use those virtual machine specifications as like a reference. And then you're trying to massage the K specification to agree with those. Now, but you agree that there's in another universe the K specification could have came first.
Yeah.
And then it would have been the job of all these implementers to adhere to the K specification.
Yeah. And that's actually the role that the yellow paper has largely played in at least the Ethereum community. It came first, and then the other interpreter implementers went and read the yellow paper. They went and implemented their interpreters, and then they tested their interpreters on the very large test set that the Ethereum Foundation puts out. But KEVM had to go through that exact same process. We had to implement our interpreter or our programming language based on the yellow paper, and then we went and tested it on the very large test set. And so we know we're in compliance with the other interpreters out there. But there are other blockchain languages that we're working on where KVM, or the K version of it is going to be the first, most of the ones we're working on have kind of two parallel specs going on, one that's in English and one that's the K spec, essentially. So there are some blockchain languages where that will be the case.
I see. Interesting. So the yellow paper was like the closest thing that the Ethereum and Ethereum Classic community had to a semantic specification.
Right. Yeah. And it's not executable. So you can't actually even test if the yellow paper agrees with all the interpreters on the test set, for example, without sitting down and writing down the state and then looking at the yellow paper and saying, okay, what's the state update I have to do, and then doing. I mean, it would just be incredibly laborious.
Yes. Okay, great. I think you've cleared up a lot of stuff for me in the audience. So why don't we close by just saying what thoughts, like what you think is going to happen in the future with KEVM, and then if you have any thoughts on the K framework in general, like if you think it's going to take over the world, whatever your thoughts about the future are, why we should be excited, interested in this. And then also there was some talk about WebAssembly. I don't know if you have any, but before we get into the future predictions, do you have any thoughts on what's going on with WebAssembly, and are you doing any work with that regarding the KEVM?
Yeah, so actually maybe the WebAssembly talk actually fits nicely into the future work talk.
Okay.
But how about I give you kind of an overview of all the future work I know about.
Okay.
Regarding K. And
okay.
So, the company, one of the companies I'm contracting for is Runtime Verification, which is tightly coupled with the research group at UIUC that does all the K research. And Runtime Verification is funded by IOHK to build up the YELE interpreter. So the YELE interpreter is one of these other VMs that the K specification will be one of the first specifications for, one of the first formal specifications for.
Okay.
That's on the Cardano network, if you're familiar.
Yes, I am.
So that's a nice example where we were able to take our experience from developing the KEVM interpreter, because the EVM, it's a lot simpler than like x86 or ARM or something like that.
Yes.
But it still kind of has some little pain points essentially that make it harder to do verification or make the specification kind of ugly or something like that. Okay. So we're really kind of trying to take those little pain points to heart in designing the YELE VM.
Okay.
And we have some kind of LLVM experts also working on that, providing a lot of advice and doing a lot of the development on the YELE VM to kind of make sure things go smoothly.
All right. I'm sorry. I missed the part about WebAssembly. How did WebAssembly come into this work?
Sorry, I'm kind of going through them in order.
Oh, sorry. Okay, go ahead.
Yeah. So that's kind of what the runtime verification side of things is doing.
Okay, good.
And then at UIUC, more just general research in K is happening. So that's more extending the abilities of K itself. So it's not as interesting here. And then for the Ethereum Foundation, I'm actually in the process of signing a contract to develop KWASM and KEWASM, or WebAssembly. And there, I still haven't fully, jumped into the water on that. I'm still kind of dipping my toes in on that project. So I'm not entirely sure what exactly their plans for that are, but it sounds like, what they really are focusing on is some sort of backwards compatibility with the EVM, where you can, take an EVM smart contract and somehow, execute it on this EWASM interpreter and get good results out of it. So I think the idea here is evolution, but it's really not clear what. I don't know if there is. I think that more experimentation needs to be done before we can be sure what this will be used for, essentially.
Okay.
So that's actually going to be over the next 6 months. One of the projects I'm working on is KWASM and KEWASM.
Okay.
So we'll see what it gets used for, but I'm the K expert here. I'm not the I'm not the smart contract expert.
So regarding a little bit more about the future. It has some competitors, which is a good thing, right? There's the technology is a meritocracy. So do you think in the future one of these solutions will win out because it's so much better, or any other reason, right? We have Haskell and then Isabelle, these other proof checkers, and the K framework. How do you think this whole part this is going to shake out? Any thoughts on that?
I think that so there are direct competitors to K, which would be like PLT Redux. Some people might argue that OTT or OTT 2 is a direct competitor. There's probably a couple I'm forgetting about, but of all the tools I've seen, none of them really scale up as well as K does. Like, we have the semantics of C, for instance, and C is a huge language. I mean, it is just massive. So it took a while to develop that, and now we're working on the semantics of C++ even, which is almost 10 times as big.
Right.
And I haven't, if you were to go and try to define this in Isabelle, I think you'd have a really rough time. I think it would just be very difficult. So while defining in Isabelle would give you the full power of, interactive theorem proving, it would just take so much longer. And then once you had it, you would have to have an Isabelle expert on hand, or maybe a team of Isabelle experts on hand to be able to use the thing.
Right.
Which, I'm not saying that, for K, you do certainly need someone who knows K, but the proving is much more automated in K. I'm not going to say it's fully automated because you still have to write the specification,
right,
and you have to write it correctly. So I would say in terms of kind of, like not fully heavyweight formal verification like what you could do with Isabelle or Coq, kind of it's kind of on a little more on the middle ground. You get the ability to do any full functional correctness verification you want to do, but it's a little bit shallower of a learning curve,
right,
and a little more accessible in terms of technology wise. So I would say K is definitely a huge contender in this field in general.
Okay. So you're saying compared to some of the other alternatives, it's nicer to use and more practical,
yeah,
if you want to verify things, check things as quick as possible.
Yeah, in terms of verification, I would say for sure. And then I would also say, like, in terms of tools that directly do the same thing that K does, like I don't want to sound like arrogant or anything, but I would say we're kind of blowing them out of the water.
Okay.
But in terms of, when you start to compare it to tools that kind of do the same thing K does, right? Like Isabelle or something like that, which they overlap a bit, but I would say largely they have different goals and they have different potentials and abilities. Isabelle's a way better interactive theorem prover than K will ever be, because that's not one of K's goals,
Okay.
But if you want to do program verification, you could reach for K and you could reach for Isabelle. And I think the spin up time with K is going to be a lot shorter.
Yeah. Okay. So definitely an important tool for the future. I have to admit, I'm still a little blown away, and I almost a little bit disturbed that you found bugs in the Open Zeppelin library.
Yeah, there are minor things. Like I can't remember exactly what it is.
See, because, okay, so I'm a security guy, or I claim I am to some degree in some area. But so the fact that security guys, the Open Zeppelin guys, that this K framework could find bugs, it's just kind of disturbing that humans can't. It's just humbling. We just have to realize that it's just so hard to write secure software, that we need tools like the K framework. And it doesn't matter if somebody like me has a PhD in this credential and that credential. It's just too hard to write secure software, right? Just winging it by yourself.
Now I'm looking back at the check. It wasn't maybe a bug, but maybe an ambiguity in the spec or something like that. But yeah, just by doing the manual verification, you're forced to encounter those sorts of issues, is basically what it was. So.
Well, yeah, but even though it was a minor thing, still, if somebody is claiming that they have secure code and they're security experts, I would like to believe that means there's not even tiny issues.
Yeah.
But I guess, okay. So, but anyway, I'm glad that.
Well, yeah, it's hard though. It's really hard to read code and be like, yeah, that's correct. That's why we have tools to do it for us. Like,
yeah. So. Yeah. Well, so anybody listening, and maybe this will help you, but another thought that came to mind is, so the world hasn't bought on to the K framework as much as they probably should. So you were able to help the Open Zeppelin guys. You're able to help the EVM developers. I'm guessing that there's all kinds of other places where you could use K framework. Somebody like you could come in with your bag of tricks, bag of tools, and really, find a bunch of issues, fix a bunch of issues, and be a hero. I would imagine there's a lot of low-hanging fruit out there. Would you agree with that?
There certainly is. We're trying to, but what we need is more people who know K. That's really what we need. So we're working on it.
Right, right. Okay, so I think we've covered. You gave a good introduction to K framework. You've talked about what KEVM is and why it's useful, and kind of what's going on, what to maybe expect in the near future. Is there anything else? Any other comments or anything else you want to say?
No, not in particular. Yeah, I think that pretty much covers largely what the KVM work is about and the K team is about. But remember, if you're listening to this and you're not interested in blockchain languages, K isn't just for blockchain languages. So.
Right, K is for writing secure software in general.
Yeah, it's a programmer's tool bag.
Yes, very good. So thank you, Everett, for joining me. Thank you for helping me to understand this difficult subject. And so thank you to the audience. Now, I tried my best to make it as understandable as possible. But if I failed in any piece of it, I apologize. So hopefully, maybe watch this. Maybe this is one of those shows you have to watch more than once to digest all the stuff. So that wouldn't be that wouldn't be a necessarily that's not against the rules. So whatever you have to do to understand this better, and then again, the kframework.org, that website. So yes, great.
One more thing I'd like to add is if you need support for KVM, we have a Riot channel a public Riot channel that you can join, and the link to that is on the KFramework/EVM-semantics repository on GitHub.
Okay, very good. All right, so thank you again, Everett, for a great show, and I wish you well with your PhD work and all your other endeavors.
Thank you.
All right, bye.